Hello, everyone. Welcome to Hoot number 50, I think. I had to close my LinkedIn because I was still getting the countdown. Anyway, welcome, everyone. It's Hoot number, I think it's number 50. Uh, Looking at the description. All right, let's say it's 50. How's everyone doing? Hey, Shaik, how you doing? It's very cold in Seattle. It was very hot in the past couple of days, but today is pretty cold. So, where's everyone from? Where are you guys joining? Hey, Leon. Hey, Netherlands. It's getting late there, right? Wait for more people to show up, and then we'll start. We'll talk about Kubernetes networking and Cilium today. So it's going to be an interesting one. Yeah, it's 7 p.m. India. Wow. France. All around the world. Look at that. Perfect. All right, well, let's get started. Yeah, 50, Shane. How about that? All right, let me switch. Let's do this view. How about this one? Abu Dhabi, Nigeria. Yeah, it's probably very hot there. uh, awesome. Well, thanks everyone for joining. It's good to see all the comments. Feel free to ask questions. I'll try to glance over to my to the StreamYard. I don't have a producer yet, so it's just me. But anyway, let's get started. So as I said, today will be all about Kubernetes networking and Cilium. Now I have to tell you, when I started preparing all this, I was thinking, well, let's just do Cilium, right? Let me investigate Cilium and do like explain what it is, do the features, do the demos, etc. But then I created the slide, right? And if you've been to any of my talks, you've probably noticed that I like to start with a definition of the technology that I'm gonna talk about. So I started doing the same thing here, but then I was like, well, like there's a lot of like talks, videos, live stream, blog posts, etc. out there that actually explain what Cilium features are, right, and go through it that way. So I was thinking, instead of doing that, let's take a step back and actually try to explain how networking in Kubernetes works, right? So because that's kind of what Cilium is trying to help with, or it's helping with. So if we understand the networking in Kubernetes, then it's going to be much easier to see how and where Cilium fits in, right? So I'm going to start with the definition, and then there's going to be a lot of networking in Kubernetes type of things and explanations and a demo, but we will get into Cilium towards the end. I'm trying to keep this episode up to an hour, but I do promise you that there'll definitely be another episode. They'll build on top of this one. So if you're here, all great. You'll get all the basics, and then in the next one, it'll be much easier to dig deeper into Cilium and understand the different features and actually understand how they work. All right, so what is Cilium? So the definition on the website is saying that Cilium is a cloud-native solution for providing, securing, and observing network connectivity between workloads, and it's fueled by revolutionary kernel technology, eBPF. So the thing that we'll start with is network connectivity between workloads and actually explain what that means. Now, as I alluded to understand that, we have to understand how networking in Kubernetes works. So Kubernetes relies on container network interface and CNI plugins to assign IP addresses to pods and to manage the routes and connectivity between all those pods. Kubernetes doesn't ship with a default CNI plugin. However, managed Kubernetes offerings come with pre-configured CNI. So later in the demo, I'll use Kind. Kind has a its own pre-configured CNI that it ships with. And if you go to any of the cloud vendors, it's the same thing, right? They have this pre-configured for you. Now, when talking about networking and communication between workloads in Kubernetes, they're at a high level. There are 4 problems we're trying to solve. So we're trying to figure out how to do container to container communication, how to do pod to pod, pod to service, and then how to do the external communication, basically bringing the traffic into the cluster, and then how does the traffic exit the cluster to access some external services. So the first one is container to container, and this is solved by pods through the use of network namespaces. So the network namespaces feature in Linux allows us to have a separate network interfaces and routing table from the rest of the system. So host has its own network namespace, and then the pod can have its own network namespace. So every pod has its own network namespace, which means it gets its own IP address and a shared port space. Now, the containers within that pod, within that network namespace, they can communicate with each other through localhost, and they share the same IP address and ports. Next one is pod to pod. Now, the nodes in the cluster have their IP address and a CIDR range from where they can assign IP addresses to pods. I'm pronouncing it CIDR, but I've read also that people pronounce it cedar. So I don't know. I'll go with CIDR, and if anyone corrects me, I'll correct my pronunciation. So there's a CIDR range. Each node gets its own, and then that's the range where the node pulls from to assign the IP address to the pod. So what that does is it guarantees a unique IP address for every pod in the cluster. Now, the pod to pod communication happens through these IP addresses. A virtual Ethernet devices are used to connect the 2 virtual Ethernets across the different network namespaces. So in this case, we have one virtual interface that's connected to the network namespace in the pod, so that's at 0. And then we have the other side of the virtual interface that's connected to the root network namespace on the node. So for each pod that runs on the node, there's this virtual Ethernet pair that connects the pod's namespace to the node's network namespace. So the traffic from one pod, like I have it on the slide on the left, right? 10.2.44.11, right? So the traffic from there will go to from ETH0 through, and it'll show up on the VET interface on the node side, and then it's going to go through a virtual bridge through the routing rules to another virtual interface that's connected to the destination pod. Now, one of the requirements of Kubernetes in terms of networking is that the pods must be reachable by their IP addresses, also across nodes, not just on the same node. However, Kubernetes is not doesn't specify nor dictate how this should be achieved. Now, assuming each node knows how to route the packets within the node, the problem that we need to be solved here is how do we get traffic from ETH0 on node 1, so that yellow thing at the top there, to ETH0 on another node on node 2. So this is where container network interface comes into play. Now, amongst other things, CNI knows how to set up or sets up this cross-node communication for pods. So if you use this output here is from the Kind cluster, right? So Kind uses a CNI called KindNet. That CNI runs as a daemon set, meaning there's one pod per node, and that pod on node is responsible for setting up that bridge between the nodes, and it allows one pod to call another pod using an IP address. So if we look at the routing table on one of the nodes, we'll see that the routing table will specify where the packets should be sent. So for example, on the slide here, I have an entry from the routing table on node 1. So this output is from node 172.18.0.2 that specifies that, amongst other things, that where the packet should be sent for pods that are running on node 2. So that highlighted line there is saying that any packets that are destined to the IPs in that CIDR range, so that's the CIDR range on node 2, right, should be sent to that IP address, which is the IP address of that other node, through each 0. And here's the more visual representation of that rule. So if you're looking at the node only, it's same as it was. But then once it comes to the bridge and goes to the routing rules, those routing rules will basically say, hey, if the IP falls under 10.244.2.0 CIDR range, then we know it must go to that IP address, the IP address of node 2 in this case. And then once it's received on that node, the internal node routing rules will know how to route it to that pod. So Alessandro is saying that he always pronounces it as CIDR. Yeah, that's what I was going originally with as well, but then it's like it's much faster if you said cider. Yeah, and cider is another thing. So is cedar. But yeah, naming and pronouncing things, it's hard. So this was node to node. I'm trying to switch my slides. Did I freeze? Oh no. Let's see. All right, this works. Perfect. All right. So the next one is pod to service communication, and service here is referring to Kubernetes service, right? We know that the pod's IP addresses are unique, but we also know that the nature of pod, right, they're ephemeral, right, means that we can't really rely on the pod's IP address, because as soon as the pod is deleted and as soon as the pod gets recreated, it's going to get a different IP address, right? So the way that this is solved in Kubernetes is by using a concept of a Kubernetes service. So when you create a Kubernetes service, what that will give you is it will give you a virtual IP address, and that IP address is backed by one or more pods. So what that means is whenever you send a traffic to that service IP, the traffic will get routed to one of the backing pod IPs. Now, for this to work, there's a couple of questions we need to answer, or we need to figure out. So first one is, how do we assign an IP address to the service? This one is fairly straightforward because we've already solved this for pods, right? So the way that we do it is we just follow the same approach. We're going to assign an IP from CIDR range that's typically reserved for services, right? And it's different from the CIDR range for pods, right? So first one is, how do we assign the IP to the service? Similar way that we did for pods. Second one is, how do we route the traffic that's sent to the service IP, and then we route it from that IP to the backing pods? And third one is, how do we keep track of the pods that are backing the service, right? We know that, as I said, pods will come and go, right? We might scale out, right? We might add multiple replicas. How or who or what updates those IP addresses? So that's solved by a component called QProxy. And there's two approaches, more or less: IPtables or IPVS, IP Virtual Server. And I'll talk about this a little bit later, and I'll show it in the demo as well. So what is QProxy? Just very high level. It's a controller that connects to the Kubernetes API server, and what it does is it watches for any changes that are made to services and pods. So whenever a service, Kubernetes service or pod gets updated, QProxy will go and update the IP table rules so that the traffic that's sent to the IP, to the service IP, will get correctly routed to one of the backing pods. So as pods get created and destroyed, QProxy will update the IP tables rules to reflect those changes. So when we send packets or requests from the pod to the service IP has a destination, let's say 1096.1.1. That those packets will flow through the IP tables rules, and as part of those rules, the destination IP, in this case, is the destination IP of the service, will get changed to one of the IPs of the backing pods, right? So the caller side will always call the service. However, the IP tables rules will make sure that to switch that service IP to the IP of one of the backing pods. And then on the way back, so when the destination pod is returning the sending a response back, that destination pod IP, right? So it's not going to be the pod IP anymore. It's going to be changed back to the service IP. So the original pod that made the call or sent the packets thinks that it's receiving the response from the service IP instead of one of the backing pods. Looking at questions, no questions. That's good. Hoping I'm explaining it well, so that's why there's no questions, or everyone already knows everything. So that's good as well. Hey, Arka, Niraj, yes, this will be recorded. This will be on YouTube forever. All right, and the last group of problems or last thing that we're trying to solve is how do we deal with external communication? So external meaning any communication that's or any packets that are exiting the cluster. For example, a pod is making a call to a service that lives out on the internet, and then any packets that are entering the cluster, so internet to service calls, right? So on the way out, the IP tables will ensure that the source IP, right, of the pod gets changed to the internal IP address of the node, right? And then typically when we're running this in, let's say, a cloud hosted cluster, the nodes have a private IPs and they run inside a VPC, a virtual private cloud network. Now, in order to allow those nodes access to the internet, we typically need to attach an internet gateway to that VPC network. And what that internet gateway does is it performs the network address translation and it changes the internal node IP to the public node IP. So what this does is it allows the response from the internet when it's coming back to be routed back to the node using the public node IP. And then eventually it gets routed back to the original caller. And on the way back, as the packets are flowing back, similar translations happen, but in the reverse order, right? So the IPs get replaced with, on the way out, it gets replaced from the pod, internal IP, external IP, and then on the way back, it's reverse. Now, on the ingress side, so bringing the cluster, bringing the traffic inside the cluster, in order to do that, what we need is we need a public IP address, right? And the way we do that is by using a Kubernetes load balancer service. So what load balancer service allows us to do is to obtain an external IP address. Now, behind the scenes, there is a cloud provider, assuming you're running in cloud, right? Or Metal LB, for example, if you're running on Kind. There's a specific controller that's going to go and create an actual load balancer instance in the cloud, right? And then that load balancer has an external IP address, and we can use that to send traffic back to the cluster. You can hook it up to your custom domain name and so on. So when the traffic arrives at the load balancer, it's going to get routed to one of the nodes in the cluster. And then the IPtables rule on the chosen node will kick in, and they will do the necessary network address translation, and they're going to direct the packets to one of the pods that's part of the service. So there's a question. So the more number of pods or cluster has, less efficient communication. Yes, exactly. And there's another like downside to using, I guess, IP tables is that everything has to be processed sequentially, right? So the more you add, the slower it is. And I think as I was researching and reading about all this, I think someone did a talk. I'll have to find that. We'll post it on YouTube later. I'm trying to remember what the specific numbers were, but there's like a lot of services, a lot of pods running in like huge clusters, and just a mere like IPtables rules updates were taking like in like hours. It's not even minutes or seconds. It was in hours. So yes, it's IPtables alone can be a bottleneck, especially they don't scale well, right? So where were we? Oh, okay. Requests coming back to the load balancer service and then to one of the backing pods. Now, if you've done any Kubernetes, you know that it's not very wise to have a load balancer Kubernetes service for every application you want to expose, because you would end up with 10s, 20, whatever load balancers and different external IP addresses, and it's going to cost you a lot of money. So what you want to have is you have a single external IP address, right? And then have an ability to serve multiple Kubernetes services or applications behind that. So the way you do that is by using the Ingress resource and a backing Ingress controller. So what is an Ingress controller? It's just a pod that runs inside the cluster and it watches the changes for changes to the Ingress resource. So when a new Ingress resource gets created, the Ingress controller will create the necessary rules to route the traffic to the correct service. So Ingress controller in this case is just like, think of it as a proxy server, right? Then when the traffic goes from the load balancer, it's not going to go to your service, right? It's going to go to that Ingress controller, and then that Ingress controller is going to route the traffic to the correct service. All right, so QProxy, I mentioned it before. So QProxy, a network proxy, runs on every node, on each node in the cluster. It's connected to the API server, and it's responsible for keeping the services and the backing endpoints, the pod IPs, up to date. Additionally, it also configures and manages the routing rules on the nodes. So when talking about QProxy, there are four different modes that you can run it in. User space, kernel space. So user space is running the QProxy as a web server and then routing all service IPs to the web server using the IP tables. And then the web server is responsible for proxying to the pods. This is deprecated, I think. They're mentioning that it should not be used anymore. Maybe it's not deprecated, but it should definitely not be using it. Kernel space, that's a Windows only mode, and it's an alternative to the user space mode for Kubernetes on Windows. And then we have the IPtables and IPVS. So the IPtables mode of running QProxy solely relies on IPtables, and this is the default mode. And I'm looking at my notes here. I have those numbers here that I was mentioning earlier. So there was a test that they did, and I'll link to the source, I guess, a 5,000 node cluster with 2,000 services and 10 pods each caused at least 20,000 IPtables rules on each worker, right? So that's a lot of rules, and it takes a lot of time to process all this. Um, Hence, IP tables don't scale well. A more performant alternative is the IPVS or IP virtual server mode. IPVS supports multiple load balancing modes. We'll see in the demo shortly. The way that IP table does load balancing is by randomly routing to one of the not randomly routing based on probability to one of the backing pods, whereas IPVS supports like round robin, least connection, destination source hashing, and so on, which means that it allows us to spread the load more evenly and effectively. Now, IPVS mode still uses IP tables. However, when we're in the IP tables mode, all the changes are made in the IP tables. Whereas when we're using IPVS mode, the IP tables just consult the IPVS for any moving parts, right? So all the moving parts are basically stored in the IPVS side. All right, so let's go to the demo. Let me read this question. Piyush, how the load balancer gets in public IP address? Does it have a fixed rate? So this is solved by the cloud provider, right? In that case, right? So the cloud provider is the one who's gonna provision a load balancer for you in a way that they provision load balancers for you. However, if you're using let's say kind with metal LB, for example, then when you set up metal LB, you can say, hey, here's a CIDR range for load balancer type services where you can pull an IP address out of it. All right, let's do stop presenting, present, share screen. Let's do this again. And I think it's this demo. Just have to move a couple of windows around. Let's move this one down here. I hope it's visible. Let me try to. I don't want the top part to be cut off. So let me move it a little bit. Is this gonna help? All right, I think it's helping. I'll move my face away. Actually, let's do it this way, maybe. Oh man, I don't want to be spending so much time on this, but okay, I think it looks good now. Let me know if it's not looking well. So another question: can we have two services with thousands of pods along with some management pod, which is multiple services with few pods? Yeah, I mean, you can have as many, whatever the limitations are. I don't remember what the actual hard limitations are, right? But you're gonna have two services with 1,000 with some management, which is multiple. Yeah, I mean, you can scale up your Ingress controller if that's what you're asking, right? You don't have to have a single Ingress controller pod. You can scale that up as well, and then your applications, right? You can scale those up as well. Hope that answers the question. All right, so let's go to the demo. So what I'll do is I'll set up. Oops, let me go this way. I'll be using a kind cluster, and I'll set up. Let me see if I can make it's a little bit bigger. Yeah. So I'll just set up a kind cluster with a control plane and two worker nodes. Note that I'm not specifying anything else because the default configuration for kind is to use the IP tables mode, right? So let's do that. Let's move this all the way up here. And then we'll do kind create cluster, config, and then you pass in the kind IP tables YAML file. So this might take minutes. So will this reduce the requirements to update the IP tables since the same pods will? Yeah, so the IP tables, the rules will change every time you scale up or scale down. However, even when you're sending the request, when the packets are being sent, the IP tables are traversed sequentially, right? So more rules you have there, the longer it's going to take, right? And I'll show the IP table rules shortly, so you can like see how big those can get. And I'll only have a couple of replicas. All right, so we have the cluster. So let's see. It's kind, and we'll just get the nodes. There you go. So we have control plane. We have 2 workers. So what I'll do is I'll deploy HTTP bin, and I'll scale it up to, let's say, 3 replicas. And then we'll wait for this to, it's still being created. Do the wide so we can see where stuff is running. So I have 2 pods will be running on kind worker, and 1 pod will be running on kind worker 2. So what we can do, because I'm running kind, all the Kubernetes nodes are basically Docker containers, right? So what we can do is we can go inside of that Docker container and we can execute commands. So what I'll do is I'll take, we said kind worker 1, so we'll get this one. Good this way? No. Docker exec IT. So I'll do 2 BFC. And what we'll run here is we'll run IPtables, list them. We'll look at the NAT table, and we'll just get the text. I'll make this a little bit smaller. So this is how the IPtables rules look like on the node. Now let me. This is all of the rules on that one node for basically 3, well, 2 in this case, because we only have two of the workloads running on that same node. But this is how it looks like, right? So there's not a lot of workloads, but there's a lot of text here. So you can imagine how this looks like if you have 1,000 services or 5,000 pods or workloads, for example, right? So if we start at the pre-routing chain, you'll notice that the traffic is going to get routed to the kube services chain. That's saying all, right, from anywhere, destination and sources anywhere, go to kube services. So if you go down to kube services, we have a couple of entries here. And what this chain contains is it contains rules for each service that's running in the cluster. And you can see that from the comments here, right? So these were comments that were added by the QProxy, right? So there's a kube system, kube DNS, Kubernetes, and then we also have our HTTP bin service there, right? And what this one is saying, and this is the name, random name of the chain where the traffic should get routed to. So I'll highlight this one, right? So what this is saying that we don't care what the source of the packets are, right? However, we do care that the destination IP is this 109 IP, and this is the IP address. If we look at the service here, notice the 1096.27.10.9. So this is the IP address of the Kubernetes service, the HTTP bin service. And then the last portion here, it's TCP DPT 8000 specifies that this rule is going to apply for TCP traffic that's destined for port 8000. Basically, this is saying any traffic that goes to this IP and this port. That's what it's saying, right? And what it's saying, well, if the traffic is going there, then look at this, this one. It should go and execute this chain here. So now we're down here. And what this one is doing is, so the first one is basically what it does is marks all the packets that are not from this subset, source subset. Basically, they aren't originating from within the cluster, right? So any packets not from that cluster, they're destined to go to that service, go to the masquerading chain, and then the masquerading chain, what it does is it just marks the packets with a specific mark, right? That's then used later. And what is masquerading? That's a form of source network address translation, and it's used when the source address for the outbound packets should be changed to the address of the outgoing network interface. So remember that whole internal VM IP to external VM IP, right? So instead of using internal, external IP should be used. Now the other, like if we single these out, the other three targets in this chain basically correspond to the pods that are backing the service, right? So if you look at the pods and their IP addresses, we got pods, just do wide. So we see 2.2, right? 1.2, 2.2, 2.3, right? So these are just the backing, right? The backing pods for the service. And the way that this works is it's basically saying from anywhere to anywhere, go to this, right? This specific chain. So if you find that one, where was it? This is marked. It will mark them, and then it's going to do the destination network address translation, DNAT, right? And it's just going to route directly to, in this case, this pod down here running on port 80, right? So it's once you understand how it like how everything fits together, it's not that complex to read these, but it can be very daunting if you're reading it for the first time. So this was the using purely IPtables approach or mode. So let's do let me delete the cluster. Hey Rohit, you made it. Welcome. And what I'll do next is I will set it up just quickly because I have a couple of slides more. I actually want to start talking about Cilium a little bit, but so this is using the IPVS, IP virtual server, right? And notice that I'm setting the QProxy mode explicitly to this because the default is IPtables. So let's set this up, and then I'll do the same thing. I'll scale up the deploy the HTTP bin, scale it up, and then we'll just quickly look at the IPtables rules, and you'll see that there are significantly less entries there because a lot of the IP stuff is solved by IPVS and IP sets. All right, so I can do this. This should be done soon. There we go. So I'll do the same, deploy HTTP bin, scale it up to three nodes, and then I'll do, oh, let me actually see where, we were lucky, I guess, because all of the workloads are scheduled on kind worker 2. Okay, that's fine. So what I'll do is kind worker 2, so 923 docker exec IT 923. And we'll do IPtables L and IPtables IPVS.txt. Let's look at the pods just to make sure they're running. Okay, so now we're just grabbing the IPtables that we got when using IPVS. So let's do that. And I have to change my... You can see that there's, just looking at lines, right? 64 here when using IPVS, and then 130 lines when we're using, well, maybe a little bit less because we move things around, but almost double, right? Let's say. And it looks very similar, right? So we have pre-writing kube services. We'll look at the kube services. We have the masquerading there. And then we have this match set kube cluster IP destination, right? Now, previously we had a chain that contained all the services in the cluster. Now, this time we have this kube cluster IP set. So, what is an IP set? It's just an extension to the IP tables, and it allows us to match multiple IP addresses at once, right? So we can match against a group. So this IP set then contains all the Kubernetes service IP addresses, and we can look at that. So let's do exec IT93 bin bash. Let's go into the node. I think I need to update, and then we have to install the IPsets tools to take a look at the IP addresses there, and then apt install IPset. Oh. All right, and now we can do IPset list cube, right? That's the scroll up here. Cube cluster IP, right? Cube cluster IP. And then notice there's 5 entries here. And one of these, look at the services, 236, one of these corresponds to our HTTP bin service, right? So in IPtables, these IPs are used in the IPtables rules. Now, this time, the services are stored in the IP set. And then the IPtables only reference this IP set. So anything, if there are any changes to the services or backing pods, right, it's not happening. IPtables rules are not going to change, right, because they're already pointing to this. So let me install IPVS admin tool so we can look at the IPs there. And then if we run the list, you'll notice this is our service, right? And you'll notice RR here stands for round robin. And then notice these are the IP addresses. If you look at the pods, wide 2, 3, 4, 2, 3, 4. Right. So these are the backing pods. Right. Now the advantage here, as I mentioned, is we can actually do proper like load balancing, whereas IPtables rules is just using the probability. And then whenever we scale up or scale down the deployment, so if we do scale deploy, and let's do 5 replicas, right? The only thing that's going to change is IP addresses here, right? There's not going to be any changes in the IP table rules, right? Oh, yeah. Oh, we actually nothing's going to change this time because we scaled up and 2 of them were created on the other worker. So let's do this. And this guy, yeah. I mean, you can see that it's significant difference here, right? All right. Well, have 15 more minutes. So let me move stuff around a little bit and go back to the slides. And window, this one, share. All right. So this was the last one that we stopped at, right? All right. So let's dive into CNI a little bit, getting closer to that Cilium topic that I mentioned at the beginning. So what is CNI? So Container Network Interface. So think of it as it's just a software. It's a binary plus some configuration that's between the container runtime and the actual network implementation. So the CNI project itself it's a collection of specs and libraries for developing plugins to configure network interfaces in Linux containers. So practically, the CNI plugins are just called by the container runtime whenever a container is created or container gets removed. Then the CNI plugin is responsible for connecting the container's network namespace inside the pod to the host network namespace, assigning the IP address to the container, doing the IP address management, right? And then setting up routes. The container runtime, the binary itself, takes in a configuration that's going to specify just a general network information like subsets. And then what it does, it sends the CNI commands based on the spec to the CNI plugin that's going to go and configure the network according to the configuration. Some examples of, well-known CNI plugins: Cilium, right? L7 and HTTP-aware CNI. It can enforce network policies from L3 to L7. It uses eBPF for that, as well as Envoy for L7. Flannel, Calico, AWS, Azure CNI, right? Basically, all the cloud provider-specific CNIs that know how to set up assign IP addresses, set up networking and routes in those clouds. So what is a CNI spec? So CNI spec is just a contract between the container runtime interface and the plugin. At a high level, just specifies 4 commands that every plugin has to implement. The add command that gets called when the container is created and it needs to be added to the network. So this is where IP addresses are assigned, for example, right? And the routes have to be configured. Delete command, this is when the container is deleted. So when you delete the container, the CNI plugin is responsible for releasing the resources, deleting any rules, and so on. And then check is just going to check whether the network is set up properly. And then the version command is going to return the CNI versions that are supported by the plugin. So the plugin itself is just a binary, and that binary runs on the host. It uses a configuration, as I said. It configures the settings for IP address management and any other plugins that need to be invoked. So CNI plugins can also be chained. One thing that I want to bring up here, there's also, if we go service mesh world a little bit, there's also Istio CNI plugin, right? That's not a replacement. So the Istio CNI plugin is just one of the plugins that will get called in the chain of plugins. And what that specific CNI plugin is going to do, it configures the IP table rules for the sidecars, right? So it is a CNI. Yes, it's a CNI, right? But it's one that can be chained. Right? All right, so we're almost at Cilium. Before we talk about that, I have to mention eBPF briefly. If you remember the initial definition that I showed in the first slide, I mentioned that Cilium uses eBPF, right, to provide secure and observe network connectivity between workloads. So basically what eBPF allows us to do is it allows us to run sandbox programs in the Linux kernel without going back and forth between the kernel space and the user space, which is what IPtables do. Right? So the image that I have on the slide shows the difference, like what is the difference between the user space and kernel, right? So kernel is basically the layer between the hardware and your applications. And what it does, it can handle things such as networking, memory and process management, files, and so on, right? Any of your applications are typically mostly run in the user space in an unprivileged mode, right? Meaning that you can't directly access or interact with the hardware. However, what you can do is you can access the kernel functionality through syscalls, right? Now, one of the features of the kernel is that it allows us to write these custom programs that can get dynamically loaded into the kernel and executed. So think of WASM plugins, right? Or Office add-ins, or any add-in or plugin model, more or less at a high level, which allows you to install something, load it, and then have it execute without like changing the actual kernel in this case, right? So this feature that allows you to do that is called BPF or eBPF, right? Now, also as part of this, the kernel supports so-called BPF hooks in the networking stack. So we'll talk specifically about networking. So think of a different event points or hooks where you can attach your programs, and then those programs will be executed by the kernel when that event happens. So if we talk about network packets, instead of like processing the packets through the chains and rules and the IP tables in the user space, what we can do is we can write a program and attach that program to a specific hook in a kernel. So those programs are then automatically executed. So for example, a hook when the traffic enters, right? Or when the traffic is exiting, right? So instead of writing the rules in the user space and processing them there, you do it directly in the kernel. So if you look at the diagram here, that just shows like a very crude packet flow. It looks something like this. So whenever a process makes a request, the packets will flow through the IP tables to the virtual interface and then through the IP tables on the node to reach the node's interface. Now, what eBPF allows us to do is it allows us to bypass those IP tables that are defined in the user space and do everything in the kernel with the attached programs to the kernel hooks. Finally, Cilium. We're almost done and we're finally there to the topic, right? Now, one of the features, like what are some of the features of Cilium, right? We talked about load balancing, right? So when you deploy Cilium, what it allows you to do is to ensure that there's connectivity between workloads set up, and it also can set up load balancing between services and pods. Another feature is the ability to enforce network policies. So if you know, Kubernetes ships with a resource called network policy. However, that resource doesn't have any implementation, right? So Cilium is one of the CNIs that provides the implementation of that network policy resource, and that allows you to apply policy, and Cilium is going to go and enforce them. Now, as you can imagine, as the packets flow through the network stack in the kernel, right, there's different programs that are attached, different hooks. Cilium also provides visibility into the network traffic flows, right? There's a UI component, it's called Hubble, and that one can be used to view these flows. And there's also the ability to do encryption using IPsec or WireGuard. So what are some of the building blocks when you, I guess, install Cilium? Cilium agents are, they're run as a daemon set. So there's one agent per node. Think of it like a QProxy, right? One per node. That Cilium agent talks to the API server. It interacts with the Linux kernel. So it loads the eBPF programs, updates the eBPF maps. So maps are the way to store exchange information. But it also talks to the Cilium CNI plugin and gets notified whenever a new workload gets created or deleted, right? Then on the L7, if we think about L7, Cilium agent is also the one that's going to start or launch the Envoy proxy when needed. So whenever there's a L7 policy that we create, Cilium agent is going to make sure to launch an Envoy proxy to process the L7 requests. CNI plugin basically installs the CNI onto the host, configures the node CNI to use the plugin, and then talks to the Cilium agent using a socket. Hubble relay, cluster-wide observability, it connects to the gRPC service that each Cilium agent provides, and then the operator that just does like cluster-wide one-time operations of installing things. Basic concepts of Cilium. We're going to start with endpoints. So endpoint is a collection of containers or applications that share the same IP address. So probably heard that before. That's basically a pod, right? So by default, when you install Cilium, when you create a workload, Cilium is going to assign an IPv4 and IPv6 address to all the endpoints, and then you can use either of those addresses to reach that endpoint. Each endpoint also gets an internal ID that's unique within the cluster node and a set of labels that Cilium derives from the pod or from the container, right? So the endpoint will get created whenever a new pod is started, and that's what also kicks off the creation of Cilium identity. So identity is assigned to all endpoints, and this identity is used for enforcing the basic connectivity between endpoints. the identity of an endpoint is derived based on the labels that are assigned to the pod, right? So if the labels change on the pod, the identity of endpoints will get updated as well. We know that pods can have a diverse set of labels, and not all of them are relevant or necessarily useful for identity. So things like timestamps and hashes. So Cilium allows to it automatically excludes some of the labels on your pods that are relevant already, like IO Kubernetes, beta Kubernetes, Kubernetes IO, pod template hash, and so on. But all this is, of course, customizable, right? So you can provide your own patterns for either excluding or including labels for identity purposes. And on top of that, there's also some well-known identities for like kubedns, core DNS, Cilium operator, and so on. Some of those have like 102, that's kubedns, right? 105, that's Cilium operator, and so on. All right, so we came to the last quick demo, and I'll do this very quickly since we're already at time. Let me stop. I would love to take any more questions while I'm setting this up, if anyone has any. All right, so we're here. So let me close this, exit from here, do this, and we'll do delete clusters, and we'll create a new cluster for Cilium. But what I'll do is I'm still using, whoops, let me close this. So I'm still going to be using kind. However, what I'll do is I'll set the QProxy mode to none, and I'll disable the default CNI. So as I mentioned at the beginning, right, kind uses a CNI called kindnet, but through configuration, you can disable it, right? So we can say, let's disable this. I don't want any CNIs because we will install Cilium to use as our CNI. So let's do that. So I'll do kind create cluster config kind no CNI dot YAML. So let's do this. Now in this example, I'm going to be Cilium is going to completely replace the functionality of the QProxy. However, I think there's two other modes that Cilium can run in or run with, where it's not completely replacing the QProxy, right? So you can run in this mixed mode, I guess. I don't know what to call it, right? Where the Cilium is not replacing your QProxy, right? But in this case, we're completely replacing it. All right, so this is done. So now if I look at the nodes, you'll notice that the status is not ready, and that's because they're not ready. There's no CNI. So what we'll do next is, and also see some of the pods are pending, right? Because we don't know how to assign the IP addresses to these things, right? So what I'll do next is I'll install Cilium. I'll use Helm. I've done like Helm update, Helm add, repo, and all that. So Cilium, this version, Cube system, and we're setting QProxy replacement equals strict, meaning completely replace the QProxy, setting the service host and the port address, just enabling Hubble, enabling relay. And this is something that we'll do next time, but I just want to set it up here already. So what will happen here is this will install the Cilium agent, and this will install the Cilium operator and other stuff. So I also have a CLI called Cilium, which you can use to look at the status. So notice there's still errors, right? They're still unavailable. The pods are still coming up, I guess, right? They're pending. Also look at the stuff here. This might take a little while, but shouldn't be too crazy. But one thing that you might have noticed here, there's no QProxy, right? Because we're completely replacing that functionality with Cilium. So if we do Cilium status right now, you'll notice that, okay, all is good, all is green. That's what we like to see. And then we'll do the same thing. I'll deploy HTTP bin. And you'll notice that these pods will get IP addresses, but this time the IP addresses will be doled out by the Cilium, not QProxy. Wait for this one to come up. Another thing that I want to show quickly is there's a CLI that I have like installed locally, right? This is mostly for like enabling things, installing stuff, uninstalling. But there's also a Cilium CLI running inside each of the Cilium pods. So we can do cube exec namespace cube. Oh, there you go. I've already run it. So let me just update this. 8v6b5, for example, and I'm running the command Cilium endpoint list, which is going to list all of the endpoints. And I picked the one that doesn't have any workloads there. So let's do maybe this one. Look at this one, right? So I'm just listing endpoints. I'm running the Cilium CNI that's deployed or installed in the Cilium agent pod. And if I run the endpoint list, you'll notice that there's a identity number, right, or a unique ID that's assigned to my pod, right here. So look at all the labels that were derived, the IPv4, and then there's another pod here, and notice it has the same identity. All right, we're at time, so I guess you can say I perfectly timed this to be an hour long. Hope this was helpful. And next time, I think in 2 weeks or so, we'll continue the conversation and we'll actually go deeper into Cilium, look at the different features, see how to apply policies, and all that good stuff. But this was more of a prelude to what's going to come. I hope this was useful. Please leave a comment if it was. I'll leave a comment if it wasn't either, so we can do better next time. But thank you for joining, and I hope I'll see you next time as well. Bye, everyone. Thanks, Alessandro. So for multi-node cluster, you have to install Cilium. Yes. It's good that I didn't click close yet. Yeah, so Cilium has to run on all the nodes, right? Awesome. Thanks, everyone. See you next time.